Okay, so thanks for attending this session. My name is ShireyStudios. I'm a consultant, and I work with many different customers, and there's so many things to talk about regarding LabVIEW FPGA. This was a presentation for this year. I did give a presentation last year that was slightly different, and so I'm looking to always present something, not to repeat too many things, although some things have to be said from time to time, over and over. A little bit about myself. I have an electrical engineering background. I've been using LabVIEW since the late 90s, LabVIEW FPGA since 2008. I've written a book on this subject. I've trained people, I've consulted people, I've developed things, I've kind of seen it from many different kinds of angles, from like support and, but I would say overall my preference is to use a systems engineering approach, which means that we look at things from a point of view of systems, and we break them down into subsystems, and we're looking at interfaces. And so if we can sort of isolate, say, what's happening in the FPGA versus the IQ data or the IO or whatever's happening out there, we can sort of isolate the problem and look at it, be able to focus on a specific area, kind of stay in our lane, so to speak. That's, I think, what's important about the systems engineering approach. The agenda, we're going to talk a little bit about LabVIEW FPGA and just FPGAs, just to kind of lay some groundwork. I'm going to establish, there's some things that we mentioned in the abstract for this presentation on the target differences. So I want to establish what those differences are. And then, of course, the tips and tricks are the main item in the title of the presentation. So why do we use FPGAs? And you may see them based on industry, you may see them based on the chip itself, based on the different types of problems. But from all the things that I've seen, these four areas are really what make the abilities of FPGAs unique. And so let's start from the left over here. So the one thing is determinism, right? With an FPGA, you're running in hardware. And so what you're running is, there isn't like a scheduler, there's no threads, there isn't anything that we have in the software world that may, sort of slow things down. So that's an important thing to, and that's expressed as low jitter, right? There's always jitter. Jitter on the FPGAs could come in the form of temperature variations. And then we have low latency. So we need to have something that happens and an event occurs in our system, or something happens, and we need to have a really quick response. And that's what we mean by low latency. We mean that we're able to respond, say, in microseconds, is what we mean by that, right? The real-time operating system, we're looking at probably milliseconds. Here we're kind of taking a step a bit faster, right? The third item is high throughput. All right, so with high throughput, we have, we could have, A to D converters these days are, they have the ability to capture gigasamples per second of data. You put these sensors together and you've got terabytes per second of data that's coming in. And, you could record that maybe as a first step, but really maybe you're recording a lot of zeros in there. Maybe there's information in there that we don't really care about, that's not of value. So an FPGA is really good at high throughput, and then the sort of thing that we typically do with a high throughput is we'll reduce the data. We look at the data that we really care about. And the way they accomplish that, right? So people see that FPGA clock speeds, it's 100 megahertz, 200 megahertz. I'll say, well, my CPU's at gigahertz. What's the deal? And kind of like lanes on a highway, we don't make the speed limit higher, we add more lanes. So with an FPGA, we parallelize. We can have more lanes, more paths. And so that's where at 100 megahertz, we could run gigabytes of data per second. So they go wide, right? So that's the phrase we say in there. And then last but not least, custom hardware. You may have an old piece of equipment from 30 or 40 years ago. They don't make those parts anymore, and you need to replace that exact piece of hardware. And you could make an ASIC, you could do other things. No one makes that hardware. You can't really buy it from anywhere because it was custom built in-house. So something that you could just replace. And FPGA is really good for that. I guess my favorite example with custom hardware is retro video games. You know, people can't get exactly those clock rates that you needed with those arcade games, and FPGAs are really good for doing that. You don't get any kind of the things that emulators will sort of add extra lag and delay. You can get it to perform exactly the way the arcade game worked. But we're not here for that. Another thing that's important to understand about FPGAs is the spatial aspect of them. And certainly LabVIEW FPGA abstracts that for us. But it is important, again, when you're doing more of a high-performance system, understanding that there is something spatial. There is things will have to get placed and routed at some point. It is important to just understand that, especially if you get a compile failure. Different terms are used out there. So you may hear the term software-defined radio, right? That's a product line that NI has. Software-defined radio, software-defined networking. Anything that's like software-defined typically means that there's an FPGA in there. You may also see the term reconfigurable computing, right? So in the industry, they use different terms to mean really there's some kind of a program or programmable logic. PL is another term that's used. And you think of it as, if you look at this diagram, this is certainly oversimplified, but we think of it as three major things that are happening in the FPGA. We have, in the middle, in the green over there, we have the configurable logic blocks. And imagine these, the terms they use is like C of logic, C of gates, and these logic blocks started out being really simple, just gates, as the term FPGA indicates. But that's also gotten to become more advanced, and then we have DSP blocks. We have CPUs, processors can be embedded inside of the fabric of an FPGA. So what we see as configurable logic blocks can take on many forms. To connect those, we have our programmable interconnects. And think of those as jumper wires, right? If I have my breadboard and I've put my components on there, I've got jumper wires to connect those things together, and I now can realize a specific circuit. And then, of course, we need to communicate to the outside world, so we have our I/O blocks. Traditionally with FPGAs, the I/O blocks are digital, but now we have something called a system on chip. Not now, for many years now. System on chip, the RF SoC, for example, that's in the NI VST, third generation, you'll see has analog inputs, analog outputs. So those I/O blocks are really, not just what they used to be, right? So that can be, again, typically it's digital, but it can be something else. Now, FPGAs are programmed. How do we program them? We program them with something called an HDL, right? Hardware description language. So this is a language that allows you to specify clocks and constraints and things that we typically don't need in software. This presents a few challenges. Typically, FPGAs are programmed by not just electrical engineers, or it's a subset of electrical engineers. When we develop logic to go onto an FPGA, we need to know what IP will go on there, what will remain on our host side, or on our computer, or on the real-time side. So that's another really big challenge. What do we modularize? And then anyone that's worked with an FPGA just for one day will know that there's long compile times. We're talking about minutes, hours, overnight. So these are the challenges that we face. And a long time ago, right? So we're talking 22 years ago. LabVIEW FPGA, is an attempt at solving, mitigating some of these challenges. It does work. So now NI doesn't make their own FPGAs. They use, AMD. We say AMD Xilinx because a lot of us still remember Xilinx was acquired a couple of years ago by AMD. So that's why we kind of use them interchangeably. And the idea of LabVIEW FPGA is that a lot of projects have a lot of similarities. We always want to communicate to the host. We always want to communicate to DRAM. We want to communicate to the I/O. There's a lot of common things that we need to do. So what NI did was they put together this interface, this environment where a lot of that is done for us. And we get to focus on our algorithm. What's unique about your project or someone else's project. Right? And the beauty of this is that this is supported on lots of different kinds of hardware, different form factors, different types of I/O, different sampling rates. It's not a comprehensive product slide, but just to give you a sense of the breadth of different types of hardware. And so now I've told you all these things. The reason kind of the motivation for me to make a presentation like this isn't to just tell you things that you could have just Googled. It's that, someone may know, I've worked with LabVIEW FPGA on, say, compact cRIO. And then they're now given, well, you're the LabVIEW FPGA expert. Here is a FlexRIO card with multi-gigabits, gigabyte sampling. Go ahead and work on that. And certainly that skill set will, some of the skills will port over. But what are the critical things that we need to know about when we go from one of these targets to another one, right? Certainly if you're in the same family, there's a lot of similarities. But if it's different, right, and it's something that I've seen people get tripped up. And I don't think it's the fault of the tool, really. It's such a broad range, right? Can't really blame anybody for that. So let's look at a couple of these products. So the things that you're going to look for, right? Having seen a lot of these hardware products, the things you're going to look for are data type and data width, right? This is how we interface to the outside world. The inside of the FPGA is more or less the same. I mean, the size may vary, so the amount of logic you can put in will vary, right? But that's a known thing. If it says Vertex 7 versus Spartan or something else, right? We know that. We can look up what those specs look like. That should not be a surprise to us. So we have the data type and the data width, the sampling rate, and then the data rate. Let's look at some examples. So here I have an adapter module for the FlexRIO product line, and that gets attached onto the base board. There's a board that it connects to that has the actual FPGA. And here we can see the data rate, the same parameters that I just mentioned. Data rate, clock rate. In this case, the data rate and the clock rate are the same, 50 million. That means that the data width is 1, right? So 1 sample per cycle. And then the data type from the example code itself, we see is, in this case, 14 bits of resolution, but they represent it as 16 bits. So that just means 2 of those bits we essentially ignore. And I'm just showing also the code for that, like where the data comes in is also being shown here. So you can see exactly what that looks like. And I think this is what you should do. When you start to work on a new project, you should evaluate this part and just understand it. Here we have a reconfigurable scope card. So this is a front end and works just like an oscilloscope, but you can also change the logic that's in there. Here you can see that this runs at 250 million samples a second, but the clock rate is 125 megahertz. So that means that we have 2 samples per cycle. Every cycle is going to be 2 of them. So we're effectively getting 250 million samples per second, but with the slower clock rate, right? So we've got 2 lanes essentially. And you look at the data there, the data is like an array that's coming out from each of those terminals. I'm going to try to pick up the pace with some of these, but you get the idea, right? So here we have another adapter module. This one has 8 samples per cycle. It's running at 187.5 megahertz, and that could do 1.5 gigasamples per second. And then the integrated FlexRIO, this is 3.2 gigasamples per second, 200 megahertz, 16 samples per cycle. So you see that all of this is coming each cycle, every 5 nanoseconds, we're getting 16 samples. So that's how we realize such high rates and can process that data in the FPGA. And this is the last one. But again, just to give you kind of a sense, this is a X410 software-defined radio. This here is running at about 122 megahertz. We're getting 4 samples per cycle, and each of those are IQ samples. So that's yet another different interface that we're seeing. Okay, so now, tips and tricks. So things, the persona, the person I'm thinking about when I'm making this presentation is someone who's like worked on a cRIO, compact cRIO project, and they've done some FPGA work in there, and now they're looking to use some of the products that I just showed you. So here's kind of a list of the things we'll talk about. So the first one, The first one, right? What did I just show you? I showed you, review the examples. I can't tell you how many times I've worked with someone and I say, open up the example. Or I'm using this hardware, I don't know what to do. Just open that up. That will tell you things that you really, sometimes like you can read the help many times. That's gonna really tell it to you. Now, you can look at your cards examples, you can look at the product lines examples, but you can also go outside of your product line. And I'll give you a couple of examples there, examples of the examples. Now, if you don't see an example, if you say, hey, I wanna be able to do something really specific, and there's an example that shows how to do that, maybe memory or handshaking or a specific FIFO configuration, you're not sure if it's gonna work, make your own example, right? There shouldn't be an excuse. You shouldn't just build it all and then hope that it works. That's very risky, very dangerous, right? And I would say that time spent on reviewing and making examples is always good. You always get a good return. It's something you'll use on your future projects, so don't skimp out on this part. I'll show you a couple of my favorite examples. So they kind of span across different products. The 7915, so 791X getting started, has an example that shows, and on the left here, you can see the technologies or the abilities that this one example embodies. So you can see there's DMA FIFO, there's peer-to-peer, goes across different cards over the backplane, the streaming IDL. A lot of people ask how that works. A lot of times you look at the example, it'll tell you how it works. And then SCTL is a single cycle time loop. A lot of times the people who are working in the compact cRIO may not have even seen that before. It's very, very common thing. And notice this here is running about 6.4 gigabytes per second. There's a 200 megahertz loop. So those data widths, those data paths are 16 I16s. So that's what's in that width that's going. Even if you're not using this hardware, this is a really good example to just review and understand. The X410 has a DSP, so we refer to digital signal processing heavy example, and it has a lot of really neat, all kinds of different things that we'd want to do with IQ data. So you could kind of review this example, see how those functions are being used, and see how they're being connected and so forth. Another thing that's also neat about it, it does use the conditional diagram disable, which you can see that kind of on the right over there. And what's happening there is they use that to enable and disable different parts of the FPGA VI. And that's really powerful because you can write NI has one FPGA VI for the X410, but that can be reconfigured, or you can sort of tune it to work with more samples per second per cycle or less. And it has settings for that. Of course, not all the configurations that you can specify here will work, right? So you could actually break it. You just got to know which ones you're changing. A little bit of trial and error may be needed there. Another really cool example is the 5171 multi-record acquisition. This is doing scope style triggering, some of the DSP we mentioned earlier, decimation, right? We did mention that earlier as well. And of course, the first one, the multi-record acquisition IDL, a lot of people want to use that in their project. And there's information on that, there's help. But seeing a real example is very helpful. Now, of course, if you're using a different product line, you may not even have this installed, right? So the gist of this is you may want to install other drivers from product lines that you're not using, because you can kind of peer into those even without the hardware. You can look at those examples, learn quite a bit. Okay. Number two, so covered examples. Pipelining, right? So pipelining is a way to get better clock rates. You may compile something and it won't meet timing, and then you don't have a bit file. You're kind of in trouble. Pipelining is a very powerful technique. It does use storage resources, so it will use either registers or in LabVIEW they look like shift registers, and so that's how we achieve those higher clock rates. The other thing with pipelining is that it does add latency. So more clock cycles to compute something is the cost of this. Now, again, it's kind of a balancing act. You may keep adding pipelining to fit, but then if the latency becomes too long, or too big, you may have to rework the algorithm itself. So let's say we have these two examples here. I have a multiply, one multiply, and then two multiplies at a 100 megahertz. Those pass. So that's the happy case. But what if I put some more math in there? Now I put 3 multiplies, and I compile that, and it fails. And that's, it's not like, that's it. It's not going to pass like that. So the way we can add pipelining is, so this is kind of at the diagram level, it's not at the function level. So we add these feedback nodes at each stage. So you almost imagine that each of those sections, those 3 sections now that we see, each of those is the critical path has been reduced. And we see that that's able to compile. Yeah.
Is that a single cycle time loop?
That is.
Okay, all right.
Yeah.
I get just making sure.
Yeah. In all the pipelining, yeah.
Is there any good way to tell if the timing is going to fail before you? Is there a way to tell if the timing is going to fail before you try to compile it and it tells you?
There isn't the definitive answer is when you compile. Unfortunately, some experience. Sometimes you may kind of get a sense of things as to what may fit. Pipelining can get you pretty far. The example, since you mentioned that, the example that I always like to refer to is if you go on NI's website and you look up real-time spectrum analyzer, the RTSA. So NI has an RTSA, it's export controlled, so you everyone can't just get it, but it's doing a lot of processing at about 128 megahertz. So it's doing like tons of FFTs, and the way they achieve that is with pipelining. A lot of certainly, good math and everything like that, but yeah, unfortunately, sometimes you may get a bit of a feel, but there isn't really it's hard to really look at something because there's other things that also play into this. Because when it's placing and routing this, it may put this in there and say, well, I couldn't, there was a congestion. There were other things in there, even though maybe it wasn't that complex, that sort of kept it from compiling. So it's kind of a compile is a good sort of, it's a good checkpoint, right? Kind of not a sanity check, but it's a good checkpoint to do, like a test, basically. We talk about test-driven development. It's one of the tests, I guess. With this here, it's passed. But it's also good to do a bit of a stress test, right? So, from 100, I just cranked it up to 300. And what that told me is that the maximum in this case, it's an estimate, right? So we talk about how certain are we of these. This one here says 213 megahertz. It could have done that. I mean, that's kind of, sometimes when you build something, you want to know how congested things are or how much more slack do you have. It's kind of it's a good figure to have. And the thing is, it will tell you that number only if you fail. So that's why I had to drive it up to a number, not just, so I purposely went from like 100 to 300 to a number that possibly would just, I knew it would fail, or it was a high chance. If it passed with 300, I'd be happy, of course, but I would also run the compile again at maybe 400 or 500, an even higher number. Now, those were the arithmetic functions, but the palette also comes with these high throughput functions. Now, the high throughput functions have a wizard that you can see here, which by default says it's not inside the single cycle time loop. You can see I've kind of highlighted. By the way, this is getting recorded and the slides are going to get posted, right? I've given my slides to the, but to me, it's really, I'm giving you sort of the key points here, right? So by default, it's not inside of single cycle time loop, but then we configure it for single cycle time loop, and then we see that the throughput is going to be 17 cycles per sample. So that's not really very much pipelined. And, but that's sort of like the starting point. That means that a value goes in, it takes 17 cycles to get a result, but while that's being processed, nothing can come in. It's kind of slow, maybe, I don't know. It's all relative, right? It depends on your project. But we could change that number. So we could change that to 1, which means that data comes in, we can continuously accept input data. However, latency hasn't been, still 18 cycles of latency. So that means that the first value goes in, it's going to take 18 cycles for you to get a result. And then you'll get results every cycle after that. But it's still going to take 17 or 18 cycles for a new value to sort of make it out the other end. But you're still able to maintain that higher throughput. So it's just really with a click of a button, right? We get that sort of built into that function. Yeah.
So all you're giving up there is just some wind up time for the.
That's latency. Yeah, that's latency. Also there's registers, right? So there's actual extra storage. In this case, because it's inside the function, maybe it's also putting down more. There's more math blocks that are being put down so that it can actually start. It's almost like starting to compute something, and then it's taking another value, so it's kind of starting that one as well. It's kind of like an assembly line in like a manufacturing plant. You know, you get a car out every hour, but that one car didn't take an hour to build. That same car, right? It took a lot longer. So that's pipeline. It's sort of the metaphor for pipelining. Okay, let's go on to tip number 3. Handshaking. You know, you go into the single cycle time loop. Not all of your functions will run or be able to run at, or have data available on every single clock cycle. So here we have 2 FIFOs, right? A FIFO that's a source, and then a FIFO that's a sink. You know, it's kind of receiving data. And data is going to go into that one FIFO, or it's going to come out of that one FIFO on the left. We may not have data on every cycle. And the way we handle that is we have an output valid. What's the first one is like, tells you if the output is valid, then we care about that data. Now, the receiving FIFO also has a handshaking terminal called input valid. So that's going to look for input valid. And whenever it sees input valid being true, then it says, okay, that's a value that I'm going to take that value and do something with it. Now, take a step back here. This is a circuit. So all of these wires, which are going to become a circuit, they always have some kind of a voltage level. There's always something happening there. So I could probe, if it were a circuit, that number. And it may have some value. It may have the last value. It may have zeros. It may have ones. The point is, we only care about what that value is when that output valid is true. That's the only time. So it could be true 5 cycles in a row. It could be 5 cycles with gaps. But this here takes care of that. Now, there's also another handshaking wire that we see that's kind of going around sort of from the function on the right, the receiver. And that's because what if the receiver FIFO, the output FIFO fills up? Or, there's been like a burst of data. So that ready for input will go false in that case. When it's empty, it's going to be true. It's going to say, I have room for more data to come in. And so that information gets fed back to the input FIFO. And so it allows it's almost like a traffic cop. Kind of says, hey, look, I'm full. Hold off on the data. Don't output anything. So even if the input, that function has data, it's not going to output it. It'll hold it. So there's a risk here in that, if things back up somewhere, they'll sort of back up, your buffers will begin to fill up. There is a risk of overflow in that case. But the point of this is to allow for, data integrity, right? We don't want our data to just sort of get dropped or get lost. Now, if you're seeing that you're getting consistent overflows, maybe there's an issue. We have to find out where the issue is, right? That's kind of the sort of the challenge there. I don't know if maybe we're not allocating enough computer memory to receive all this data, or somewhere there's a bottleneck that we have to resolve. Yeah, but certainly this here will keep that data. We're only going to process valid data. Now, that's a 2-wire handshaking. There's also 4-wire handshaking. 4-wire handshaking is we have the function in the middle. That's a square root function, and that function has an input and an output. So because it has an input and an output, we now have to manage handshaking from both sides. We have to handle handshaking from the input function, FIFO, and from the output. And I know that sometimes these handshaking can get really busy. My advice is to just kind of take them one step at a time. You start with your input valid, the first one. I then look at the output valid. Those are kind of like your easy ones, the sort of freebies. Kind of know where they should go. And then the others are, you see that they go back, and you see where they should be connected to, right? They're talking to the upstream and downstream blocks, right? And there is help on this. There's a I didn't include the image from the help because the help has like 4 or 5 blocks. So I thought I'd include something a little bit, easier to process and just talk about. Okay, so got 3 tips so far. Tip number 4, so review the help files. That sounds like a really weird tip because, who looks at the help for the multiply function? Like probably nobody, right? You just say like, it's multiply. Get an 8-year-old to help you with that. But with the FPGA side of things, you go into the detailed help and it says single cycle loop supported. We take the divide function, not supported. For this divide function, you can divide in the single cycle time loop. Don't forget that. Quotient remainder. People like to use that on the LabVIEW side, on the Windows LabVIEW for desktop side. What's a single cycle time loop not supported? I didn't show the usage and some of the other information, but the help will tell you, right? There was a question earlier. I'm like, hey, can we tell if this is going to fit? Is it going to, timing wise? They do give us some information in the detailed help on that really should be reviewed. And again, it's kind of this, it's a little bit of a reset. When I started to use LabVIEW FPGA, I'm still a CLA, right? But I was like, hey, I know LabVIEW, there should be no problem. And I wasn't reading this help because I said, I got 10 years on this. So why do I need to look at the help for the quotient remainder function? I want to look at the ones that I don't know. Those are some of the challenging functions that we want to look at the help. But then there's some freebies. And so, for example, join numbers function, as an example. You look at the detailed help and it says no clock cycles to execute, no FPGA resources. So again, this is where we have to think of it as a circuit. As a circuit, if I'm joining an 8-bit number and an 8-bit number to make a 16-bit number, it's the same thing. It doesn't, like the FPGA doesn't know what an 8-bit number is. It just knows bits or whatever groupings it has in its LUTs and the components. So this is really a construct for us. This just kind of makes it easier for us to read as opposed to seeing 32-bit, a bunch of wires. So it doesn't need to do anything to do that. And there's a couple of other functions that are like that as well. Like if you do like index array with a fixed value, fixed index number. So there's a couple of functions that are like 0. Nothing, you're not taking up, you could have like 10 of these things like in a row, and they're whereas in software, right, we know what that is, right? It's moving the data, it's allocating more memory, it's quite the opposite in some cases. So, read the help. Different ways to compute, sort of related to some of the previous discussions, but common thing, we want to know, hey, is something an odd number? Is a number that's coming in, is it odd or is it even? Well, some people in LabVIEW will, use the remainder quotient function, which we already saw from the help is it's really difficult. But really, if I have a 8-bit number, a 16-bit number, I know if it's odd or even by looking at the first bit. So there's a number to Boolean array, there's an index array, all of those we're just picking off that one bit. So all those 2 bottom functions use no resources. It's just a way to sort of pick off that value that we care about. And there's others, right? There's if you want to multiply by 2, you do a bit shift, or divide by 2. Those are things that you have to think in terms of the bits. Just to give you a sense, this is from NI's website. They have if you look up the intro to high throughput DSP and LabVIEW FPGA, this is like a case study where it's like a FIR filter, and what they do is they design the FIR filter and then they just keep optimizing it. They compile it, they get results, and then they kind of like change the way it's configured. Same logic, same results. And what's really neat, like sort of the bottom line of that page, which is a good page to read, is it shows you the difference that some of these different ways of computing, what benefits you can get. I mean, those functions that we saw earlier, in this case, you see it gets you max 20 megahertz of frequency, clock rate. And then we see what pipelining does. I didn't highlight that one. But then the high throughput math, the Xilinx functions, so there's like all kinds of levels of optimization. And someone may say, well, why don't we just go right to the bottom one? Why not just skip all the steps? Certainly, you use the more optimized ones. You may not be able. First of all, they may be very complex to use. And so if you don't need to go at that rate, you can we don't need to have that extra effort on the project. If 20 megahertz is enough, it's enough. I could say that, for example, the Xilinx core generator is very specific, right? So if it's that filter needs to be modified because it has very specific configuration settings, and maybe you won't be able to get exactly the type of filter you need, or maybe there's something you need to change, right? You get more control when it's actual individual blocks, like discrete functions. So, there could be a reason to be somewhere not on the extreme sides of this table. And again, this is a specific example. It's a filter. It's not like, mileage may vary kind of thing is the key thing here. Using of simulation mode. It's doesn't use as often as I think it should be. That's, I guess, what I would say. Let's put it that way. It's not in the workflow of a LabVIEW developer, right? You got your code, you hit the run button, you check it out, and kind of keep doing that. And a lot of times, people in LabVIEW FPGA, they're doing, they're like, oh, I got to compile it again. I got to compile it again. Stop doing that. Simulation mode is something we can set at the target level. You can see that from the graphic here. You right-click on it, and you can set that. I would say, first bullet there, it's critical to workflow. I mean, you could take a project, the project could take months, years. I mean, it could be almost like untenable. And if you're not using simulation. Now, not everything simulates. So for example, those IO nodes that I showed you earlier, those don't simulate. Peer-to-peer doesn't simulate. There are certain pieces that do not simulate. And so what's the answer to that? The answer to that is to modularize. Make my example. So if I have peer-to-peer and I'm doing some functions, I'll use an example to fully understand how that part that won't simulate and that peer-to-peer or whatever that part is that I don't doesn't simulate. So I make a separate example for that sort of proves out how I'm going to use it. And then for my blocks that can simulate, I make a sort of standalone, like a test bench, and I study that. I could put my own test signals in there. And by the way, those that are working with Vivado, like the HDL languages, this is a no-brainer. They don't even think about whether this is like part of their workflow. It's just that typically someone coming from a software background, it just won't be in their workflow. That's really what this is sort of highlighting. So I think this would apply also if you're doing cRIO work. It's really for all the projects. And certainly this is there to mitigate that risk, those long compile times. So if you see the compile times are still long, maybe you need to further modularize. It's a tool that has to be, you want to maximize the use of simulation. Simulation also doesn't require hardware. So if you've got a team of people that are working on some IP, you can have them all work. They don't have to all be on the chassis. They could be doing this on a virtual machine or on their laptops. You could be waiting for hardware to arrive. You don't even need to have the hardware to run simulation. So what we see when we're running simulation is you'll see that you've got like sort of your host VI and then your FPGA VI at the bottom over there. And you could probe it. A lot of the debug abilities that we have in just, sort of LabVIEW for Windows desktop are available to you. And when you're doing that, you could probe and so forth. Now, while you're in simulation mode and you're using these probes, I think this one's a really lesser known feature, sampling probes. So now when I right click, first of all, I have to be in simulation mode. I then make sure that then I go and right click on a wire. We all know about probes, right? That's kind of right there, close to what I've selected. But then there's something else that we get in LabVIEW FPGA that's a sampling probe. So when you click that and select, FPGA is the option there, you get this sort of logic analyzer look. And when it runs, when you simulate, when you run this, when you run the host project and host VI, and then in turn that runs the FPGA VI, you're going to get this logic analyzer. So it's a really great way to debug, because just seeing a single probe value, this is something that's changing over time. You may not see exactly what the error was, or what the bug is, or what's causing the issue. Maybe those handshaking wires that we mentioned earlier, if the handshaking wires aren't connected correctly, data is getting stuck somewhere and it's not moving. So this could help you identify exactly where that's happening, and all without compiling. That's really the big thing. Now, we've simulated, we've debugged, we've done all the things that we could have done to mitigate the risk of, we don't want to compile and then realize that I wired a subtract function incorrectly, like something so trivial, right? It's a real shame. But now I've compiled it and I've put it into hardware, and I want to do sort of like I want to be able to debug it in hardware, right? I want to see or something is happening differently, right? Because it runs at data at full rate. Something is just happening differently. So I see sometimes people will put indicators in different places. So here's a way we can catch overflows, right? I've got some logic over there, but I'm looking to see if an overflow has occurred. Now this here is the wrong way to do it. This here in hardware, right? If this is updating 40 million times a second, 200 million times a second, no one's going to see that. And it just blips once, nobody can see that. Not the host, not people, nothing. So what do? We should latch that value. So we put a latch function. There's two forms of that I'm showing here, two examples of it. The idea is to just keep that in mind. So I can latch that function, latch that output, so that way if one overflow in this case occurs, this goes true, and I then know that value, I can then see that on my host side. I can check for that, but because I've latched it, so it could happen once in those, at 200 megahertz, we'll still see it. We can also have it inside of a case structure, and sort of, when that goes true, that's when it gets updated. So we can actually have some different, we can get creative in terms of how we capture these values, these sort of static values. Another thing we could do is we can also count events, right? I mean, I could tell you that, hey, an overflow occurred, one or more overflows occurred, but what if I want to count that? What if I want to know how many occurred? So there's a counter function, and I connect that to the same terminal, the same Boolean input, and that will tell me how many have happened. Now, maybe that's running out of control. It's really running. There's lots of overflows happening, or maybe just 2 or 3 happened. Or maybe it's when a specific thing happened and you saw that. 1 or 2, just sort of overflow. Yeah, question?
Yeah, those functions, the latch and the counter, they used to be kind of hidden, like many years, like 8 years ago or something.
Yeah.
Are they like in a place on a palette where you
you got to look for basic elements. Basic elements is what they're called. And, that's a tip I didn't include, but some functions are, you may find them, the palette will vary based on the target type. I think it's based on what they've tested, but it is certainly, that's where it is good to just know, now all of these exist on disk.
Yeah.
So a real pro tip, it could be, I don't know if it's a pro tip or if it's a workaround, you can also know where those are located on disk and just pull those right in.
I'd say that's a pro tip.
Okay, yeah, we can add that as another tip, right? The bonus. But these are functions that, really, really powerful for debugging. Right, and I've shown for static capture. Right, these are things that are, we're not looking at waveforms or signals. These are really good. And you could maybe come up with your own. Based on what I've mentioned here. But you want to be able to capture certain things. It's almost like imagine you're testing an electrical circuit and you've got an oscilloscope. You need to capture something that happens, trigger or somehow configure the event to capture things at a specific point in time. That's kind of what we're doing here. What if I have a whole bunch of signals, right? I just want to know how many. I want to know when the overflow occurred. I want to know maybe when that overflow occurred, what were the other signals doing? What were their values? What had happened before that? So something maybe a little bit more dynamic. So it's like a collection of signals, and I want to see it from one cycle to another. Now, in the AMD Xilinx Vivado world, they have something called the Integrated Logic Analyzer, ILA. And that's a block that you can put into Vivado, and it allows you to sort of capture data and do this exact same thing. And a common request, people are, whether they're LabVIEW users or they're, coming from the Vivado side of things, they'll say, hey, I really want an ILA in LabVIEW FPGA. And ILA itself probably won't be, you can't use that block directly just because it needs JTAG. There's some other things where it's kind of not available to us. I'll bottom line it for you for that. But the ILA is essentially a block memory that takes up some resources on the FPGA. You connect up some wires and signals to it, and that block memory is a FIFO essentially. It gets FIFO'd over to the host, and you receive data on a per cycle basis as to what's happening. So LabVIEW FPGA gives us those tools. You can make a DMA FIFO, target the host FIFO. You put that on your FPGA code. You do, not a fancy term, it's bit packing, right? You take all those bits, all those signals, numbers, whatever they are, you sort of bit pack them into like a U64 or some kind of a number, some kind of a value. You put them all into that number or that value, and every cycle, you're just sending that collection of information to the host. That's effectively what the ILA is doing. Now, on the host side, we read that and we have to know how that was written to and how that was put together. So we know how to sort of unpack that and just turn that into a waveform. And we can then see exactly how that's running. Some things that I'm not showing here, if I'm running at, again, 200 megahertz or 50 megahertz, that FIFO can fill up real fast. So we may want to add some additional logic to this to, sort of open up the pipe, capture, when I push a button, it'll just capture, say, 50 cycles, 5,000 cycles, a finite number basically, right? You want a specific amount of signals to be seen. Now, what if you need a lot of samples? There's projects where people have used the DRAM. You can actually use the dynamic memory that's the DRAM that's part of the FPGA board. So it's not on chip. You can actually FIFO that data into the DRAM and have gigabytes worth of data captured. And because that's at the clock rate, at the hardware rate, you have to make sure that that's not overflowing. You have to sort of debug the debugger. But that's something where you can capture really large amounts of data. Now, I see the hand. 1 second. Now, sometimes the error may happen within a few cycles. You may not need to see billions of cycles to see the error. Hopefully it's happening. You figure out a way to cause that error to happen with less cycles than a couple of seconds worth of data. Yeah.
Oh, I was just going to say, so you fill up the RAM, the DRAM, and then you can just slowly, it's slow, but you clock it out.
So we say slowly, just it's at its own pace. It's at its own, it's not because the hardware is going to sort of come in, it's going to be it's like a fire hose kind of data, yeah. Especially like X410, it's like a lot of data coming in. So you can use the DRAM. And the DRAM has, I don't have that as a tip here, but you can use the DRAM has a configuration where you can have it set up as a FIFO. So you configure it as a FIFO, so the interface into this is not all that different. You don't have to manage addresses. Yeah, and there's an example for that, by the way. Remember, tip 1. Tip 1 should be like 10 tips, but it's really, that's the tip. Kind of a lot of it, all of these things, of course, are related. And what we see in this example is, we see these values. We know that the single cycle time loop was running at a set rate, and we're capturing values at the hardware rate. Now, this, of course, could also be used in simulation mode. I certainly framed it as a hardware thing, but this could have been used in simulation mode as well. There's no reason why we couldn't have done that. Sometimes I overrun, but I think here we've got a few more minutes. Some honorable mentions, I guess. Fixed point math. Fixed point math is, why do we use fixed point math? So you got integer math, you got floating point math. The difference between integer and floating point math is an almost order of magnitude of logic usage and process and time, like cycles. Whereas fixed point math gives you the ability to have fractions, but at the rate and resource consumption of integer math. So that's why we use fixed point math is popular with FPGAs. Now, that doesn't mean that FPGAs can't do floating point. The same silicon that runs a GPU is being used, the same fabs are being used to make FPGAs. So you can do floating point in FPGAs for years, for many years. Just that if we want to be more, some people, if we're building something that's going to fly, maybe they want to be more power efficient. We can do more, right? So that's where, the sort of default with FPGAs is like fixed point math. So that's another extra skill to be developed. Generally, the skill that gets developed with fixed point math is a range analysis. What's the range of the data here? What's the range of the data here? And so forth. And that allows us to specify how big the fixed point value is going to be, like a number of bits. You have to specify that, how it's going to be configured. Now, for us, we're dealing with sensor data. We know the range of that data that's coming in. And now the other thing is, if I multiply that data, if I do something to it, you're going to see the bits get bigger. But a lot of times the bits, it's just noise, right? If I acquired 14 bits of resolution, from a 14-bit A to D, just because I multiplied it and now I have a 28-bit number, or I don't now have 28 bits of resolution. So somewhere in those 28 bits, I can actually just chop stuff off and just keep it at 14 bits or maybe 15, just kind of give it a little bit of, room for overflow, things like that. A lot of times the math is done at, they normalize the data to 0 to 1. So that way if it's normalized 0 to 1, it's not going to grow as much. So there's, again, you use simulation to sort of understand the fixed point math. It's not going to be hundreds of compiles. Use a simulation, you'll learn how fixed point math works. The second one, sometimes I work with people and they say, we're going to, compile time is like, X for 10. It's like compile time is like 3 hours, maybe more. They're like, yeah, we're going to figure out a way to make that 10 minutes. It's like, that's not going to happen. Doesn't matter if you have like tons of computers. You may shave off a little bit on that. But I generally treat the compile time as kind of like it's a fixed thing. Now, if your compile goes from 3 hours to like 18 hours, maybe you did something that, maybe we can remove something for now, kind of put that in later. Maybe there's some modular, we can, what I'm saying is, if I put all the logic in there and now the compile time takes a really long time, maybe I want to work at it kind of piecemeal. And at some point you will need to do that longer compile time. So there's things that we do to indirectly optimize for compile times, but directly trying to figure that out, I don't think that should be like the primary goal of one's project. Like it's you're kind of chasing the wrong sort of the wrong thing there. And the last one over there, that's compile results may vary. That's a really kind of could be scary. So if I run the same compile, the same logic, the chip. We can realize the same logic in different ways. That chip is, especially if it's not full, it can put the logic in different places and give you effectively the same clock rate, the same resources, the same everything. So you'll see different compile results, different compile utilization. It'll meet everything, all your requirements, but you will see that sometimes. And the Vivado tools give you the ability to, there's a randomizer, basically there's a seed that gets set. And LabVIEW FPGA, we don't get that access. We don't get access to that. But with those tools, because there are some industries where you don't want to have every recompile give you something different, they can actually lock that down. I would say that in test and measurement applications, we're not building stuff that's the FPGA part of the test and measurement application is not like flying or doing something that's safety critical, typically. So, if you're doing that, that's a Vivado export. That's a whole other discussion. It's another feature. So it's just good to be aware of that and not to try to like really study, I ran it once and it was 10 and then it was 12. And, it's a thing to sort of, it can be noise, I guess. And then I'd say the last one, if you see a project that took a couple of months in LabVIEW FPGA and you see the amount of code that resulted in, it may not actually look like a lot of code. Whereas like if you spend like 3 months writing LabVIEW or any other software language for that matter, you can generate, thousands of lines of code, lots of code. But here, a lot of the effort, most of the effort I would say in the FPGA world is planning and designing. making sure that this is the right thing that you need to build. You're putting the right things in there. Remember that first slide where I talked about the things that the FPGA does, the high throughput, the low latency? If your project doesn't check at least one of those boxes, maybe an FPGA is not needed. So we want to make sure that the things that we're putting in the FPGA are things that fall into those columns. So that means that, to me, that means opening up LabVIEW and starting to code is sometimes the wrong thing. So a lot of upfront work, a lot of design, a lot of review, maybe some test compiles, right? We go back to the question of like, hey, how do I know if it's going to fit? That's a thing that we'll do to sort of, before we're really beginning development, right? We're kind of like understanding, understanding things. And in fact, I didn't, it's a buzzword, so we have to mention it. People talk about digital twins. And, when you simulate, that's a digital twin. The FPGA world's been doing that before digital twin became, in vogue. But that is essentially what we're doing. There's a digital twin that's been created, and we're running that to see how things will respond. In fact, we could also make a digital twin that's purely software. So it's taking the same inputs. Of course, it's lower bandwidth. We take the same inputs, the same outputs, and that's our digital twin. So that should be able to give us the same results that we're going to do in hardware. All of that is extra planning and design that happens. Are there any questions? You've been raising your hands, which is great. Okay. No, good. Okay. Yes.
Yeah, I was talking a lot. So.
I thought I'd wait to see if someone else wanted to say something. On this fixed point growth of bits, so you're doing adds and multiply, and it goes from the 16 to 32 or 44 or whatever.
Yeah, it grows.
I experienced that once, and I don't know, I was kind of disturbed. I tried Googling a bunch of things, and it seemed like you needed to be an electrical engineer to decide what method or what approach to use. But maybe you could explain the 0 to 1 normalization a little bit more that you mentioned.
Well, some of the functions, their input will be 0 to 1. So they're expecting a 0 to 1. So like if you want to do a certain, I don't have the functions here, but some if you look at some of those high throughput math functions, but their input range is 0 to 1.
So you take your 16-bit value and
you
change it into 0 to 1, like have a scaling kind of a thing?
Yeah.
Okay. All right.
Yeah. What did I... Yeah, so let's say you've got like 48 bits. You see the function down here at the bottom. You can extract all the bits from that function. Like let's say this was 64 bits coming in. And now I can access all the bits. I use a array subset function. And with the array subset function, I can grab, maybe the significant bits are now, 5 bits in, right? So I've got 64 bits, 64 bit on the block diagram, but I really care about 16. So I put maybe it's the first, I don't care about the first 5 bits, but I care about bits 6 to, whatever the next 16 bits are. I just do an array subset of that number, of that array, of that Boolean array. Again, and that costs you nothing.
Okay, yeah.
And then you place it. That's not, I don't know how much of an electrical engineering question that is. It's more of a math question. You will look at that data and you will say, oh, these numbers are always 0. Or, you have to sort of.
You could just kind of. You can watch the data and get to know it and go, I can see a pattern.
We're close to out of time, but I'll tell you, very first project we worked on with LabVIEW FPGA was an algorithm that computes pi. It's called Buffon-Veneto. So it's random numbers, you put them in there, and it gives you a result. So when we had the fixed point value set incorrectly, the first time we ran it, we got, and of course we know the answer to pi, so it's kind of an easy one to verify. First time we ran it, we got 2.8 zeros, all zeros. So we probed it and made a correction. Then we got 3.1 and zeros. So we sort of slowly corrected where the bits were being sort of moved and used. And then at some point we got, 9 digits of pi, whatever digits of pi we could get. So in your case, you would have some real live data and expected results. And you would kind of say, oh, it's clipping.
Yeah, it was
RF
data.
Out, sorry?
So that it was RF data that I was dealing with, and so I thought, I'll put some aliasing or artifacts or some weird stuff if I do this wrong.
but you should be able to get it bit for bit equivalent. Yeah.
Thanks.
Yeah, great questions. For more information, well, I don't want to keep anyone from presentations, other things. Some more information. There's last year's presentation that I gave is on YouTube. There's a presentation. The second one is during the pandemic, they did something called VI Week. And so a bunch of us got together, people in the community, made presentations. And so I did something kind of similar to this, because it is an important thing to talk about. And there's some other things in there. There's a LabVIEW FPGA examples. That's a NI open source thing that I'm sort of, we're plugging examples into that. And again, these slides are going to be available. Thanks for those recording this and supporting that. And enjoy the rest of the 2 more sessions there,